Okay. Okay, so I've decided not to torture you anymore with more of the random variate generation stuff, although I have lots more to talk about that, but I do want to move on to our ultimate and final topic for this course, which is output analysis. So what what we've covered so far and what you have in your toolkit is kind of a concept of how this discrete event simulation stuff works. You have a methodology in event graphs for designing one, and without having to worry about the specific implementation. There are either two implementations of this. Some of you are using the Java one, and others are using the Python one. And even though there are some slight differences in adjustments that have to be made with respect to the implementation, I hope you're getting a sense that the advantage of having a methodology independent of the implementation allows you to kind of have complete flexibility in that. So in other words, if there's another language that becomes very popular, or one that you prefer that isn't one of these two, then basically all you need is just a way to handle the events and to generate the random variables. And if you have that, then you can basically take any event graph and turn it into a running simulation. And so so you have a methodology to design the simulation. You have an implementation way to implement it, including ways of generating whatever random variables that you want. And so so that should give you the ability, in principle, to create kind of any discrete event simulation and actually execute it. So what does that leave? Well, that leaves kind of what, given the ability to do that, the question arises, like, why? Haven't really asked that question too much. In a way, those of you taking the course, or the answer why is because the instructor, some SOB makes you do all this stuff. Okay, but the bigger why, and why do any of this in the first place, is to find out something that you didn't know beforehand. In other words, there are always there are questions that arise when you're either analyzing a situation, trying to find out something about it, maybe considering a system that hasn't yet been built, and one, or in a system that already exists. In some of the models that we've seen, questions come up like, well, how many machines should we buy? How many servers should we hire? How much capacity in the waiting room should we build? Things like that, just from the queuing types of models that we have. In the most recent ones, and especially the latest one that I've kind of dumped on you, you have the ability to create scenarios where you have entities that at least move around in a two-dimensional space and interact at least a little bit with each other. And so, questions of, scenarios, wargaming, things like that can kind of come up. That is, if we perform this operation, what is the probability that we will have some kind of success, however that success is defined? So all this to say that the when it comes to simulation of any kind, whether the kind we talk about here or even the ones you talk about in the other classes, they are never ends in themselves. They're always a means to an end. And in the case of the ones that we're discussing in this course, they're primarily used for analysis, as I said way back in the beginning. Analysis meaning that I want to find out the answer to a question that I don't know the answer to. If I already know the answer, then there's no point in kind of doing this. Unfortunately, it's also true that a lot of times the models are used not to find out what the answer is, but to somehow justify a predetermined answer that one has. That's obviously a misuse of this. And it happens, but it shouldn't. So kind of, I guess that's kind of the dark side of some of this stuff. So up until now, we've been running our models once. And so that kind of falls under the realm of basically sort of testing your implementation to make sure that it's kind of working okay. But the values that we've gotten so far are not ones we can take to the bank. Why? Well, because there's randomness. And when there's randomness, you can't just do it once. I mean, here's just as an example. I have a coin. And let's say we're going to flip a coin and play for dollars, heads or tails, whatever. What do you want to know about the coin? Is it fair? Are all coins fair? Not necessarily. Okay, so how can you, what do you want to find out about this coin? I want to find out what is the probability it's going to come up heads. So if I run a stochastic simulation once and try to have some meaningful conclusions from that, it's like saying, I want to estimate the probability of heads, and I flip the coin once, and it comes up heads. So what's the probability? Is this a fair coin? How useful was that experiment? Well, I mean, I got some information. It came up heads. That means it's not a two-tailed coin. That's all I know. Running a simulation, a stochastic simulation model once is like doing that. That's why we have to kind of talk about this, talk about output analysis. That's the term. And now, you've all had statistics, so you have some basics in kind of what's going on with that, what random samples are, you know about hypothesis testing, you know about estimation, and especially you know about these things called confidence intervals. Hopefully your statistics class talked about that. And we'll talk about why a confidence interval is important, and hopefully your statistics class also was honest with you about what a confidence interval means, because it's kind of tricky. When it comes to the data that comes out of a simulation, however, we immediately run into a problem that isn't faced by your statistics class. What is that problem? Well, we'll get to what that is. Okay, so what is output analysis about? The objective is we want to learn something about the system being modeled. These discrete event simulations, they're typically stochastic. You know, they don't have to be, but they typically are. Stochastic is a fancy word for random. And so if you want to impress your friends, use the word stochastic. Because I never use a large word when a diminutive one will do. Okay, so hopefully I've convinced you that one replication is not representative of a system, you know, such as the probability of heads. So what kinds of things might we be interested in? Well, the main ones have to do with estimating means. So kind of hearkening back to our basic queuing models, things like, what is the average waiting time for customers? So if I'm interested in what my customers' experience is, then that's something I might be interested in. Or if this is like a processing facility, what is the average time to process a job? Whatever that means. So whether it's in a single one or like one of the transfer lines that we have, or is it something called a job shop that we didn't get to, but is kind of a more complicated version of that. Or like in our reneging models, what is the average percentage of lost customers due to reneging? When we ran the model once, we got a number, but how representative was that number? Was that close to what that average is, or not? Okay, so again, single replication is not sufficient. And if we want to estimating the mean is one thing. There are but it's not the only thing. We might want to estimate things like quantiles. We might want to estimate the standard deviation. Why? Because it's often not enough to address the mean, but we want to know how variable things are. So again, thinking back to statistics, if we have a random sample, the minimum variance unbiased estimator of the mean is the sample average, if we have a random sample. Sort of put a pin in that. And hopefully your statistics class convinced you that was not enough, because just like running the model once doesn't give us any idea of how accurate that is. Even running it multiple times and estimating the mean still doesn't give us any idea of how accurate that mean is. And that's where confidence intervals come in. So this is all review, hopefully. So from statistics, if we have a random sample, and remember what a random sample is. A random sample is a set of independent and identically distributed observations, or random, kind of before, it's like, this is where human intuition about randomness kind of is not exactly ideal. And before we observe our sample, they're random, but after we observe the sample, it's deterministic. In other words, before I observe this coin flip, assuming that this is a fair coin, I don't know whether it's going to come up heads or tails, but I can, if this is a fair coin, the probability of each is 50-50. If it's an unfair coin, then I might, maybe the probability of heads is 0.55 and tails is 0.45. Either way, I can characterize the probability of that. But after I flip it, okay, this one is tails. After I flip it, it's not random anymore. That's why you always want to bet on the horse races after they've been run, if you can. And that's why they don't let you. So. Or like, let's see, but there's an old movie called Guys and Dolls. You ever see Guys and Dolls? There was a gamble. He had dice that he wanted to play craps with, but but he filed off all the dots, but he remembered where they were. So okay. So back to, a random sample. So before we take it, it's random, and after we take it, it's not random anymore. So so beforehand, what we can do is we can a point estimator for the unknown mean. So this random sample again, they're identically distributed. That means they all have some common mean. And if we want to estimate that mean, a point estimator for that is just our regular old mean, where we add them up and divide. And an estimator for the unknown variance is this the sample variance, which is just the sum of the squares of the deviation from the mean. And then there are various divisors depending on one's proclivity. 1 over n is sometimes used. 1 over n minus 1 is unbiased in a sample. You remember, did they show you all that stuff? There you go. And I mean, another way of looking at it is losing a degree of freedom when you estimate the mean. But that's just kind of fussing. In practice, one of the nice things about simulation, as opposed to the statisticians are oriented towards physical experiments. And in physical experiments, your observations are fairly expensive. Those of you who are, some of you will be doing a human factors thesis, and you will learn, in a human factors thesis, you will be getting people to kind of either use your model and evaluate it, or evaluate their performance on certain things. And so the number of people that you're going to be able to use is relatively small. When it comes to simulation, we can literally run millions, if not billions, of replications. So in simulation world, observations are cheap. And so in a cheap observation world, these kind of fusses about n or n minus 1 become moot. Okay. So now, under modest assumptions, an approximate confidence interval now is what we do is we have our sample mean, we have our sample standard deviation, which is just the square root of our sample variance. We divide by the square root of n, and then multiply by this weird thing here, which is a t quantile with n minus 1 degrees of freedom. And then we have this extra alpha, which is our, typically alpha is like 0.05 or 0.01. Where did that come from? Probably the same guy that invented 30 as the normal. When I say under modest assumptions, this is strictly true only if our random sample is from a normal distribution. If our random sample is from a normal distribution, then this literally holds. If it's not from a not from a normal distribution, then this is not true. So they lied to you. However, there is something which, the cavalry that rides in here is something called the central limit theorem. And did they talk about the central limit theorem? Yeah, okay. Central limit theorem says that if we take under, again, mild assumptions, if we take enough of a sample, then this sample mean is approximately normally distributed under, again, certain mild assumptions. And so this approximately holds, even if our underlying sample is not normal. There are exceptions to that, but those are kind of pathological. My experience is that in this kind of simulation world, for the kind of measures that we get, all those assumptions are met. Okay, and all of this is review. So you all know this, right? But remember this assumption right here of a random sample being independent, identically distributed, because that kind of bites us a little bit. Now it turns out that there are actually kind of two. There are a few more, but you have to kind of be weird to kind of create those. But in practice, there are two ways of analyzing this, because the nature of the data that we get is different. And those are terminating and non-terminating. Okay, a terminating simulation has some kind of natural end or condition. So, for example, if our simulation is like a combat scenario, then the ending condition is typically, when one side wins. And that can be anything from, like a force on force type of thing. And often, like there's some kind of ending criterion, maybe where one side kind of loses a certain percentage, or like a maneuver type of situation where do the friendly forces get to the objective by a certain time? But that's a natural ending condition. Another natural ending condition is if we're modeling a facility that kind of just runs, doesn't run continuously, but kind of opens in the morning and closes sometime in the afternoon or evening. So that's a quote natural ending condition. So if we open at 9, we close at 5, then that's kind of the end. And those are called terminating simulation. And sometimes we can induce, because the reason why natural is in quotes is because we can induce something. Like we might be interested in the first 1,000 customers. And so that's not necessarily a natural ending condition of the simulation itself, but it's an ending condition of what we're interested in studying. On the other hand, there are non-natural ending conditions for a simulation that just kind of runs and runs and runs. And for such a and almost all of the queuing models that we've created are of that form. In other words, you just kind of run them and they just kind of keep running and running and running. And so for those, there's no natural ending condition. And so it turns out that in those situations, there are kind of two possibilities. One is it reaches steady state. And we'll talk about what steady state actually is, because steady state is not something fixed in a stochastic model. Rather, it's a situation where the probabilities become stationary, or it blows up. So an example of it blowing up, and you may have encountered this in running some of your models, if generally speaking, for a queuing-like model, if the arrivals are happening faster, at a rate faster than the service rate, then the queues will just blow up, because eventually, the queue will reach infinity, but eventually every particle in the universe is going to be waiting in your line. And in the model, that can kind of happen. In the mathematical model, that can certainly happen. In the simulation model, what will happen is you'll eventually run out of space on the computer and it will crash. But those are the only two possibilities. If it doesn't do that, then it will it'll keep running, but it'll fluctuate. It'll fluctuate in a stationary manner. So, and it turns out that there are issues with dealing with each of these, not the least of which is that the data that we're getting are not, remember I kind of said, put a pin in this assumption about a random sample. So let's say our basic data consist of the delays in the queue for each customer. That's some data we've been getting, right? So that's some data that we can try to apply to that. So what is the problem with just sort of directly applying that data? Well, first of all, they're not independent and they're not identically distributed. But other than that, now, is it obvious that the delays in the queue are not identically distributed? Maybe it's not obvious. All right, so let's do a little thought experiment. So let's just say that have a single server queue, and we've been running it sort of starting empty and idle. So the first guy that shows up, what's their delay in queue? 0. Now the second guy who shows up, what's their delay in queue? Exactly. So the second guy has a certain probability of it being 0 and a certain probability of it being something greater than 0. It depends. So the first one is always 0. The second one, it depends. So right off the bat, the first and the second one have a completely different distribution. In fact, that second distribution, notice, is one of these mixture distributions that I was talking about earlier. So there's a certain probability that it's 0. And if it's not 0, assuming everything else is continuous, it's going to be some other continuous random variable. But what about the third guy? Well, it could be 0. Is that going to be the same as the second guy? Well, probably not. So in other words, they're not identically distributed. Okay, so remember, our random sample is independent, identically distributed. All right, so are they independent? No. Okay, why not? Exactly, yeah. And just even moving beyond the first guy, so so let's look at sort of the 10th guy. The 10th guy versus the 9th guy. Let's say if the what does independence mean in part? Independence means, among other things, that if I know the value of one, then that gives me no information about the second. So coin flips are presumably independent. So if I flip the coin, a fair coin, and I got a tail again, now does that affect my next flip? So no. So that's independence. I mean, assuming I'm not kind of, there are people who can kind of flip a coin and make it come up a certain way. That's not me. Okay, so that's independence means if I know that I flip, even if I flip 10 heads in a row on a fair coin, what's the probability I flip a head on the 11th one? Still 50-50, doesn't affect it at all. That's independence. Or I mean, that's a consequence of it. Independence is more than that, but that's a consequence. So let's say that customer number 10 had an extremely long delay in queue for whatever reason. What about customer number 11? Does that give us information about, do you think they're going to have a long or a short, or is it not going to matter? Well, yeah. I mean, a lot sort of depends, but it's like, what does his delay in queue consist of? So there was a certain gap between when that person arrived, but the guy ahead of him had a really long delay in queue. So the next guy probably spent a lot of time sitting behind him. Now, supposing the 10th guy had a really short delay in queue, supposing his was 0. Does that give you information about what the next guy is going to be? Is that going to be bigger, smaller? Is it going to be like the previous one? So, yeah, exactly. So when he went in, he went right to the front of the line. And so really it's just, he just has a service time in front of him. Whereas in the other one, the guy's sort of sitting there forever. In other words, what this means is these delays in queue are not only not identically distributed, not independent. And that is typical of the data that we get from simulation. So what does that do to our analysis here? So the very first assumption that statistics makes for doing its analysis is that we have a random sample, and we do not have a random sample. It's random, but it's not a random sample. It's not independent or identically distributed. So what can we, so we conclude is that typically the individual observations are not independently identically distributed. That is not a random sample. Yeah. Yeah. In fact, exactly. You're absolutely spot on. And that's the dilemma. In other words, the average delay in the queue is not a well-defined value in that setting, because each customer, starting from the first one, has a different one. And so if I have observations, all of which have a different mean, then if I say, what is the mean delay in the queue? What is the average delay in the queue? That has no meaning. In other words, so it sounds okay, it sounds good, but it doesn't mean it. It has no meaning because they're all different. And so, so what can you do? Well, what you can do is you can say, what I want the average of the averages. That is, what is the expected average delay in queue over, let's say, over a single day, or over the first 100 customers? Or what is the maximum number in the queue over the day? That would be another thing I'd be interested in. Or the average number in the queue over the day. So in other words, in order to even define the thing that I'm trying to estimate, I need to kind of be really careful about defining that. And that's usually something that kind of gets glossed over, because if I have a random sample, if I have a truly random sample, I don't need to worry about that because that's well defined. But here it's not defined. And so but these are. So the average delay in the queue over, let's say over a day, that's the one value that we've gotten, or the average number in queue over the day. Remember there was a time average that we had. That is a single value, and that is well defined. That is, what is the average number in the queue over the day, or what is the average delay of customers over the customers we encounter in a day. So so it's like we have to do some work just to even define what it is we're trying to estimate. So, so the normal statistics cannot be applied typically to the raw simulation data because it's not in IID. And so as I've hopefully convinced you, like successive delays in the queue are not identically distributed and they're not independent. Okay, so what can we do? Well, we can do with exactly what you were suggesting, which is the thing we're trying to measure is say the average. So let's say we're rather than the whole day, let's say over the first first 100 customers. And so for that, we can get a mean, an average of those. And what that is that's one observation of the expected average delay in queue for the first 10 customers. That's one observation of it. So what can we do? Well, we can run it again independently. And we can repeatedly run it for, let's say, capital N. And here's the thing. Now, remember when we talked about random numbers, how if it's truly random, or at least is random enough, then for the first replication, so let's say if this was our random number sequence, and for their first replication, we used these values. And then for our second replication, we picked up where that left off and then used these values. Then what we've done is we've performed an independent replication of the same experiment. And whenever you perform an experiment, whether it's a physical one or a simulated one like this, you want to have the same conditions, identical conditions, but something be different. So if you're doing a human factors study, and you have your experimental protocol, so you bring one person in, you have them do that, and then the next one you give them the same protocol, but it's a different person. So the randomness there is the person. So here we don't have another person, but what we have is we have this random number sequence. So if I don't shut down my virtual machine, but I simply pick up my random numbers where I left off, then I get an independent observation. And if I start with the same initial conditions using the same parameters and the same model, then I will have an independent observation of that same thing. And what is that same thing? That same thing would be, say, the average delay in the queue over the first n customers. And so now I have a random sample. So these means are independent. They're independent because I was careful, well, hopefully careful to use a different sequence of the random number stream, which is as independent as the random number variables are. And it's identically distributed if I use the same parameters, the same initial conditions, and run it at the same protocol. That is, if I'm running it for n delays in queue, use starting empty and idle using exactly the same parameters. And so my estimate of the expected average delay for the first n customers is the average of the averages. And because they're independent, I can now form the estimate of the variance. And it's a true estimate because of the independence. In the stats class, did they talk about why, if you have a correlated sample, that this estimate of the variance is Verschlagene? That's a technical term. Maybe if we have time, we'll look at that. Not today, though. Okay. So our our mean of the means is our point estimate. Our square root of the variance is our estimate of the standard deviation. Now we have the square root of capital N, that is the number of replications, not the little n. And then our T statistic, capital N minus 1, 1 minus alpha over 2. That's our confidence interval for the expected average delay in queue of the first n customers. So kind of having experienced some problems with the data, we now have this sort of a solution to that. And the challenge, the biggest, and actually this is, as you can tell, this is fairly straightforward. I won't do it today, but the next time we'll kind of show how we can go about doing this. I think you can just sort of imagine it. In the when we run our model, if you remember, we said the event list or schedule would say, we say reset, start simulation. Basically, all we need to do is we just need to wrap that in a for loop, and then make sure we collect our statistics carefully. I'll show you the specifics of that when we meet again, not today, but next week. And notice that we could do this also for things like the average number in the queue, which would be a time average, but the replication, notice the replications are always going to be a tally. So even if the underlying observations are from a time varying value, because we have a discrete number of replications, then that's always going to be a tally. So what we're going to do on this, what we have to, if you think about what's necessary here, we are collecting our statistics for the run using one of these simple stats guys. And so what we need to do is have a second one that collects statistics from the individual replications, but then we need to make sure we clear out the statistics from one replication to the next, otherwise the data gets contaminated. And we'll talk about what that is all about next time. And I'm ending a little early here today, but that's what I have here. So you can read about it in the reading. You can start reading about this. We're gonna look at the terminating case. Now this is the terminating case. So we begin and run it for until some kind of ending condition. One of the characteristics, and we'll talk about this more, of the terminating case is that the initial conditions play a role. They affect your results. And that's in contrast to the steady state one, which is a little more involved. In the steady state case, we can define what we're estimating much more simply because it's typically just a single value, but how to come up with our that is a bit more challenging. Anyway, so we'll look at that. Again, the lab will be online on Zoom today. I've hoped to the latest computer assignment is it's a little more involved because I wanted to do the sensing thing for you, but that involves referees and mediators and sensors and all kinds of things. They're a little more complicated. So I have a longer due time on that, a week from tomorrow, and it's kind of worth twice as much, so because it's a lot more work. So, okay, if there are no more questions, we will